So today I wanted to give sort of a quick recap or state of the union on how we can import from different ML frameworks into IREE, and then pick up with the IREE pipeline of choice. And yeah, some disclaimers. So if you notice that there have been developments in the projects that I referenced, then of course it's possible that I've missed them. So feel free to raise this. Also feel free to make points and ask questions throughout. And there has been a similar presentation by Max Bartel, also here in the meeting in last year at EuroLVM, but this time we're mostly focusing on bringing the model down to the IREE level, as it's what presumably interests most of us in the call. So just do I navigate? Okay. Just as a quick context of why myself, as someone who works at Turfline, is interested in the topic at all. We basically see the how disjointed edge AI hardware and frameworks for developing ML models are, and therefore for potential clients of products that are, for example, based on IREE and MLIR, or basically any inference framework, the velocity is something that they're looking for, because any new model or any new hardware is very difficult to adopt. And basically what we at Turfline try to do, leveraging IREE, is unify all the frameworks and chips for edge AI deployment. So focusing in on the more technical level, let's just quickly look at the landscape of ML frameworks that we are trying to support also in IREE. Let's walk through a few example paths for lowering from those frameworks into IREE, and well, as probably all of you know, also into upstream ML dialects that are heavily used in IREE, first and foremost LiteRT and TOSA. I will be giving some examples of how craft level dialects, so-called craft level dialects, can be useful, and we'll conclude on what could be further done in IREE going forward, so that the import part from different frameworks into some unified MLIR representation could be even more convenient, especially for newcomers to the project. Because as it stands, when you're either onboarding into MLIR as an enthusiast and want to try compiling some ML models with any MLIR stack, not necessarily with IREE, you're essentially you don't know where you should go, because the whole ecosystem of tools that you need to use to go from one of the possible ML frameworks to something where you could play around with compiler passes and transforms is very disjointed and could say scattered. There's a lot of projects, obviously, that are based on MLIR, that if you want to try multiple things, you have to build all of them and somehow keep track of which version of LLVM project you're using under the hood. So IREE definitely helps here, because already as it stands, some of the importer flows from the most popular frameworks are definitely made easier by IREE, and by the fact that it has input adapters for some high-level dialects that basically, one way or another, allow to minimize the number of dependencies that you have to have on top of IREE to use IREE comprehensively for compiling the models. And then we can basically take a look at a few examples of how this can happen. We'll cover LiteRT or TF-Lite. Please bear with inconsistent terminology here. what it looks like with ONNX as well. Then Torch as like a very complex case out of these two, and also, well, highly popular, and JAX, JAX as I guess the ML framework that I have the least experience with, but we'll just look at this as an example. So LiteRT, just skimming over it, quite popular, especially when we're considering mobile and edge use cases compared to TensorFlow, sort of big brother. Quantized models are definitely a key area of interest when we're considering TF-Lite models, and therefore it's important to have some convenient way of bringing TF-Lite models into IREE. And as of now, this flow has solidified in that the TOSA MLIR dialect can be used. TOSA itself as a standard is also a hardware standard, but thanks to let's say the semantics of the operators that are specified by TOSA, and thanks to the MLIR ecosystem around it, it has become rather easy to go from a TF-Lite flood buffer into the TOSA dialect of MLIR. And this has been greatly simplified as of a few months by now by Artem publishing a standalone lightweight package for going from TF-Lite flood buffer into TOSA MLIR, which can then be backed up by IREE. And the beautiful thing about this is that the TOSA converter is, as I've said, it's a standalone tool that you can just download from PyPy, and you don't need to build TensorFlow from sources, which you sort of had to do once it's been removed, once the support for this kind of lowering has been removed out of the box from what was available in the main TensorFlow repository. So you basically had to build those tools to go from TF-Lite flood buffer into MLIR and then into TOSA, which on its own wouldn't have been, let's say, too bad. But then we remember that the purpose is to be able to then use IREE or any other MLIR compiler. And this means probably different versions of the LLVM project, because TensorFlow as a project is a way larger project than just this subset that we're interested in the context of TF-Lite MLIR-based flows. Let's say there was limited influence that one could have on what version of LLVM it is based on, and then you're reaping all the incompatibility fruits. So the current status is basically solidifying towards using the TOSA converter for TF-Lite from Artem for the LiteRT models. And from there, IREE is able to consume the TOSA MLIR directly because TOSA MLIR is supported as the in a form of an input plugin within IREE. So far from our experience of using this flow or similar flows, admittedly, we still have to conduct more testing for more models with the ARM provided TOSA converter, but it has been quite stable, especially thanks to TOSA being sort of stable as well as a specification. The IREE pipeline for in real cases where you have actual models from LiteRT come in, and sometimes you have to, it doesn't necessarily work out of the box, as I've illustrated. Sometimes you have to provide additional options to the input stage of the IREE flow, because not all TOSA MLIR validation will necessarily succeed otherwise. There's also certainly some things that are not very easily expressed in TOSA MLIR, simply because, again, of the standard itself from real-world models. Symbolic shapes and things like this can cause all kinds of issues. And this, of course, kind of negates some of the benefits that you get from the simplicity of just downloading a simple converter and then hoping that it will just work out of the box for every model. Not necessarily, but in principle, in our experience, this is a very convenient way of supporting and testing LiteRT models, especially integer models. And this is basically what it's solidified as for LiteRT. Let's carry over to the next framework. And as of now, the most stable importing flow for ONNX is based on Torch MLIR, which as is ironic, probably doesn't surprise those with more experience of the IREE Torch MLIR ecosystem. But it's definitely the flow that, in our experience at least, is the easiest to use and has the broadest support. Torch MLIR as such is already part of the IREE dependency graph, so not having to rely on any other projects or support something within IREE is definitely a plus when we can basically have 2 for 1, have ONNX along with the Torch flow. And under the hood of IREE, there's basically invocations of Torch MLIR buses that could also be potentially replicated with just standalone Torch MLIR. The way it works for ONNX is that first everything gets lowered into the so-called ONNX Torch dialect, which is really, I guess the best analogy I would have is custom name DOPs. But the good thing, which allows for this whole thing to work, is that ONNX as such, ONNX graphs are quite similar to the A10 format, which I believe, correct me if I'm wrong, but it kind of originates from Executorch. And this compatibility basically allows to support conversions from ONNX flavored Torch dialects into the actual Torch A10 dialect of MLIR, which is then basically can go down any lowering path towards a dialect like TOSA, linalg, and also the IREE extensions for linalg and all the mechanics of a full execution of an ML model. So with, of course, some caveats that some things are difficult to support. Sometimes some of the newer operators, let's say group query attention, which has only recently made it into the core ONNX specification, you have to facilitate a lot of conversion routines, and I mean, throughout you have to test the correctness through this gradual lowering through multiple dialects, whereas Torch MLIR as a code base can be quirky. Because the Torch MLIR project itself has not originally been this sort of front-end sandbox. It also contains some backends. And as it was gradually being repurposed, historically speaking, some of the artifacts, such as a huge switch statement for basically all ONNX operators that is split into 3 files, can be difficult to extend, but this is something that works and also is not completely impossible to use. There's an alternative flow. I'll be honest, I don't have much hands-on experience with that, but basically ONNX MLIR, as developed by IBM, is also an option. There is stable HLO, a stable HLO flow that you can then use to import into IREE. I'll touch a bit more on this in a second, but we should bear in mind that trying to use ONNX MLIR and especially trying to keep things compatible if you want, let's say, to support to run multiple ONNX models with a regularly renewed IREE project, if you're doing some development, well, then another dependency isn't really something you want when you can have everything with Torch MLIR. And yeah, I thought it's worth mentioning stable HLO with a larger focus. It's a dependency of Torch MLIR and IREE. Anyway, IREE supports import from the stable HLO format. So it's rather convenient to use even if you're relying on, let's say, the last tested flows for ONNX or anything else. As it stands, IREE consumes stable HLO quite well. And it's another example. Stable HLO is such of a what you could consider craft level dialect, which doesn't stray too far from the model graphs where they originate, which in turn makes it easier to test the lowering towards something like linalg and IREE extensions around it. So yes, if we are to consider the experience that we've had in our team with ONNX models, the Torch MLIR path is basically very usable, somewhat difficult to extend, but the single dependency factor is very convenient. One thing that you have to bear in mind, of course, is that depending on the actual models that you're using, if those are large to any extent, you may run into different restrictions, let's say of the protobuf format, with the need to make sure that the weights are stored separately, exported from the ONNX model file. And well, in the tooling with which is based on Torch MLIR, you basically have to implement this on top, or depending on what kind of experiments it is that you're running with IREE, let's say, you have to do some things manually. So this is not a problem that's solved out of the box. But other than that, our experience with ONNX has been quite decent. Let's also go over PyTorch, which is actually the most complex case simply because of how PyTorch fits into the whole ML development ecosystem and how it has to be usable from, say, the wider, from the viewpoint of the wider Python world. It's highly popular, so of course there's something that needs to be done in order to bring PyTorch models into IREE. Otherwise, well, we would probably had less interest in the IREE project. And the task itself is rather complex because of how complex the torch graphs can get. And there are, of course, caveats that, for example, some of the cases that are possible in PyTorch, let's say a control flow based on the specific values of the tensor weights, will not be possible to trace when you're trying to construct some different representation of the model graph, which will cause a graph break, and therefore can be a little bit difficult to really support all of different PyTorch models that can be thrown at you. if you're experimenting, let's say at the stage of experimenting with IREE, you should be fine though using the Torch export functionality and then the effects importer functionality in Torch MLIR, which will generate the same Torch A10 dialect. And you also have IREE Turbine as a project that has been maintained for quite a while, but has been more quiet recently, which would encapsulate potentially the whole flow from PyTorch export stage into the IREE pipeline. I think we could just call IREE Turbine and be done with it. But again, depending on what it is that you're trying to do, Torch MLIR could also be used directly. The effects importer in Torch MLIR will basically try and construct the Torch dialect from a case like this, where you have some relatively simple graph with dynamic shapes. This is taken just from Torch MLIR lit tests. And yeah, Torch MLIR also gives you further ways to try out different pipelines. To construct the pipelines, you can go to stable HLO or to TOSA, as exemplified here, just using a Torch MLIR opt command. And well, since Torch MLIR is relatively well integrated into the IREE flow, you can also just consume the result of the effects import into IREE, compile IREE opt, and be in a position to just compile the model further with, again, the pipeline of your choice, or however it is that you've configured the buses. So in our experience, it's not an easy problem to solve, as I've already said. Effects importer can allow to support some advanced features as well, but ultimately, with things like craft breaks, as I've described, there are some limitations. Torch to linalg, which is what basically Torch to IREE also equates to, is from our observations sort of better tested than Torch to TOSA. And there are still some artifacts when working with Torch MLIR and trying to extend it, where it can be a bit difficult to develop, same as for ONNX use cases, but it's entirely possible to also develop this project further. Also experimenting with Torch, with the TOSA-based flow for Torch. Be aware that some operations and the preferred shapes, preferred layouts can differ very much, so you'll end up with a lot of transpositions and reshapes and whatnot, which, depending on the what you're trying to support in your pipeline, what it is that you experimenting with, can just sparkle some edge cases, which is maybe not a bad thing, because you will have an opportunity to fix some things in the IREE patterns or upstream MLIR patterns. JAX, just touching briefly, as I've said, I'm do not have like much hands-on experience with JAX, but basically, if you want to support some JAX models with IREE, you used to have IREE JAX as one of the ways to do that, but the last time I checked, that project wasn't very actively developed, to put it mildly. So with JAX ecosystem basically allowing for a stable HLO export, you can then consume it into IREE, as I've already shown previously with maybe some ONNX examples. This is also what you could use. As I've said, Max Bartel had some experiments with some basic JX examples, and according to him, the coverage was good. So this is the state of JX in the current IREE ecosystem. It could definitely be supported better if there was interest, and the stable HLO path would look appropriate, I would say. So apologies, there's something missing on the slide, but basically, let me maybe, put some pointers wrong slide in the presentation. For the LiteRT for TF-Lite, as it's also widely known, the integration into IREE exists for the TOSA format itself, but then you have to rely on the TOSA converter for TF-Lite, TOSA converter for LiteRT, in order to produce the TOSA MLIR. ONNX through Torch MLIR, you can also say that it's well integrated into IREE, because what you have to do is basically use the Torch MLIR passes for consuming the ONNX flavor of MLIR, and from there you can basically just call IREE. Torch, as we've discussed, once you've figured out if the model that you're under test is exportable, then you can export this, and Torch MLIR provides an effects importer. You can, from there, also rely on the IREE tools or Torch MLIR tools directly to consume Torch MLIR, and JX into stable HLO. You have to produce the stable HLO, and then hopefully the coverage of the input conversion path in IREE for stable HLO won't let you down. And the common theme that I see here is that there's room for further unification, so that even though, I guess, compared to the state where different ML frameworks and the tooling was a couple years back, you can already make do with less dependencies, with, let's say, Torch MLIR handling both ONNX and Torch, with no longer it being needed to build TensorFlow from source to support LiteRT. But still, in terms of pure UX that you have with IREE tools, there is potential for further development here. And we could seek to use the TOSA and stable HLO dialects more to maybe unify to some extent what comes out of the different source level ML frameworks. From basically the models themselves, you could use stable HLO and TOSA dialects to try and unify this a little bit further, and it would make sense to further develop IREE where we have better UX, and also maybe IREE dialect, IREE dialects, extensions for linalg, and, well, of course, linalg and tensor dialects themselves would not be the first level where all of the input frameworks get unified. That's basically it. It was Artem from Roofline here, overviewing the different ML frameworks, the way that you can support them in IREE. In general, feel free to discuss things offline on GitHub, Discord, and all of that. But luckily, we also have the opportunity to discuss some things around framework imports here directly. So off to Q&A.
Thank you, Artem. That was a really informative and great talk. So Andrzej has the question. You can just go ahead and ask Andrzej.
I pressed the wrong button, I'm sorry. But I do have a question. So if I wanted to, so okay, there's a lot of frameworks. By the way, thanks for the summary. Really, really interesting. And I think it's important to have these summaries because there's just so much and it can be very confusing if you're new to this. So I think it's very valuable to have an overview of what the options are and where to go. However, I wonder, you mentioned a bunch of projects. Now, if I were to use one of them, if I say wanted to take a JAX model or a PyTorch model, can I assume that most of popular models will work? And if not, is there any place where I can check what works and what doesn't? My expectation is that things will not work. There'll be things that are tested and they do work, stuff that doesn't work. Now, how do I know where to start so that I start with something that is guaranteed to work? Like, is there any public CI anywhere or anything anywhere that you could use to like gauge, manage your expectations basically?
That's a very good point. Overall, thanks, Sanjay, for the question. So in terms of public CI, what IREE as a project supports right now is some. There's basically an IREE test suite which is currently being extended with some smaller state-of-the-art models. I think it's ResNet, a couple others. Maybe Roberto in the call could actually correct me because I think there was a PR from Roberto in this. But in general, I don't think there's like a clear list of what's supported by IREE org, which is something that is very much something that we I think should be done going forward with the IREE project, because it's also not that you necessarily want to have to go to a CI repository or to open GitHub Actions and grab for state-of-the-art model names just to understand if you're allowed to try out some model. I am also, to be frank, I don't know if there's a good way to make sure that everything works with all the frameworks and all the tooling. As I said, some of the flows, let's say here for JAX, are kind of more experimental, but in theory, we could also develop the UECI to a point where, let's say, we have a stable HLO example, which is exported from a JX model. So I think while a few state-of-the-art models are guaranteed to work just by the sheer testing coverage that exists in IREE and Torch MLIR, you're right that public lists would be next good step. Max?
Yeah, just to comment on that. So it is a huge amount of compute you need to test this out, and like we feel that internally every day. But in general, like from our experience, T-Flight is the most stable one if you want to try out. And Torch, like most often fails at Torch export. If you get past Torch export, then very often it works with IREE. This is our experience. But Torch, like there are a lot of graph breaks because people write just Python code that does not trace in Torch models, and this is like the biggest issue there. And then kind of ONNX sits somewhere in the middle there.
Just to add to that before I take your question, Juan, basically, let's as Max said, it's also a call for action on everyone's side, I guess. Obviously, having something out there that just like guides you through what is supposed to work is really nice, and we're trying to expand the test suite to actually account for that. Although if you actually get past like Torch exporting and then it fails through IREE, that's a call for action that you can create issues, let us know, and we can take a look together always. So if there's a problem, or if there's something that has to be supported, and even before that, if you have a model that you would want supported, you can raise it as an issue in IREE, even if it doesn't trace export, we might be of help, let's say. Obviously, as long as we could, to the best of our abilities, but we could come up with a solution together if some new state-of-the-art models are what it takes to make you guys happy. So yeah, in that regard, Juan, shoot.
Yeah, I also wanted to add to that. Many Hugging Face models, especially like new implementations, they have or modules, they have a property which is exportable, and many times is hard-coded as false. So you can also, even before reaching IREE, you can tell if something will be friendly with exporting in Torch.
Any other questions from anyone else? I don't seem to see another one, but I'm gonna actually ask one regarding those graph breaks, and this actually probably relates to those Hugging Face models that are marked as unexportable as well. But actually, how do other like frameworks that have to do some sort of like tracing on the models handle this? For example, like Torch Compile, I think Torch Compile does actually allow you to do graph breaks, but how does, for example, like Executorch or other frameworks handle this? Do you have an idea, or?
On Torch Compile, I wouldn't really come up with the answer in the spot. I haven't used it. Maybe Thomas could chime in.
Yeah, also not much knowledge on like Torch Compile specifically. I know in IREE Turbine there is like some like experimental IREE thing, I think, to go through Torch Compile, and then the graph breaks wouldn't be so bad anymore. But anyways, I just wanted to comment on the Executorch side, I think, because it's like the most relevant, I guess, and they also rely on exporting modules, so it would be the same ingestion IREE uses. And as far as I know, or like at least partially for some models, I think they also contribute to like Hugging Face and so on to make it more export friendly. And then they also have like their own model zoo where they just say, oh, if we want to support, let's say, X state-of-the-art model that's currently not tracing in Hugging Face, they just rebuild it in a way that's traceable. And so it might also make sense, let's say, if you have like some model you want to run it, if you can see how Torch Executorch exports it, it will most likely also like go into IREE, the model that's exported there. But yeah.
Also, if I understand correctly, like it basically takes like the data dependent branches on the like Python code side and just like rewrites the model in a way that it is actually like traceable, and then uses those models to actually like get it into the framework itself.
Yeah.
Okay, makes sense. Thanks. Next.
Yeah, for Torch Compile, so what they do, they basically also export a graph, but subgraphs of it. And every time there's a graph break, they execute the Python code. And then there are cases where the inputs change to the compiled graph, and then they have a recompilation going on. So, for example, when you vanilla use Torch Compile on a Hugging Face model, you have like a prefill compilation step and then decode for the first token, and then for the second token, because now it recognizes their dynamic shapes, and then from there on you use the compiled model. So it's kind of Python wrap around this whole process, just tracking subgraphs of FX graphs.
That makes sense. Thanks. So, are there any other questions?